objective for this assignment is to understand one of the digital modulation technique. Second, to generate the pulse code modulation using MATLAB. Lastly, to plot the pulse code modulation signal using MATLAB. What is pulse code modulation? It's essentially analog to analog conversion of the spatial type directed information contained in the instantaneous sample of an analog signal is represented by digital words in a serial bit stream. So here, the equation 1. And this is the output for figure 1, which is analog signal and sample signal. And this is for figure 2, which is encoded and decoded signal. And lastly, this is a square signal. Example 2, this is the code in MATLAB. Here is the result for figure 1. And this is for figure 2. Next, for question 1, what is the frequency of the analog signal that has been used in the example 1? So here, the time period is 100 and the amplitude is 1. So we use the formula frequency 1 over time period, and we get 1 over 100. So it is 0.01 Hz.
Next is the question 2, which is we have to generate a 2 kHz sinusoid with a peak-to-peak voltage of 2 volt, where is positive minus 1 volt, and generate a quantized signal when n equals to 8 and n equals to 16 levels. After that, we have to calculate signal to quantization noise ratio SQ and R. From the coding of the example 2 given, we just set the interval of time exists to t equals 0, 0.00013, and then we change the message signal function x equal to sine 2 times 2000 times pi times t, and then we declare n equals to 8, which is the quantizing value, and just add the exist 0.001, negative 1.25 and 1.25 inside the figure 1 and figure 2. So we run the code. The output for n equals to 8, which is figure 1 is signal using compending, while figure 2 is signal without compending. After that, we change the value of n equals to 16 and then run the code. So this is the output for n equals to 16, which is figure 1, the received signal using the compending, and figure 2, the received signal without compending. Next, we are required to calculate the SQ and R. Firstly, we have to calculate the dynamic range for n equals to 8. The small letter n is equals to 3, so that the dynamic range is equals to 20 log 2 power of 3. So the value is 18.06 decibel. After that, we are required to calculate the SNR, which is SNR is equal to 1.76 plus 18.06 decibel. So we get the value of SNR is 19.82 dB. And lastly, the SQNR, which is 10 log 3 times 2 power of 3 squared, and the value is 22.83 decibel. Next is for n equals to 16, so the small letter n is equals to 4. The DR is equals 20 log 2 power of 4, so the value is 24.08 decibel, and the SNR is equals to 1.76 plus 24.08 decibel, and then the value for SNR is equal to 25.84 decibel. And the SQNR for n equals to 16 is 10 log 3 times 2 power of 4 squared decibel, so the value is 28.85 decibel.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sarah binti Muhammad Kamal with metric number B0820100004. So for question 3, we will convert the function from MATLAB into block diagram in Simulink. In question 3, is given task to use Simulink. From example 1, first we open the Simulink and we click the library browser, then we browse the signal generator, and we drag to this part, and I set the amplitude to 1 and the frequency to 1 in unit hertz. Then browse the path generation. We browse the path generator as a square signal, and we set the amplitude to 1 and the period to 1/10, which is the 1 over frequency, and we set the path width to 15. Then we browse the third product if kidnapped in from the signal generator and the path generator. After that, I browse the scope 1 and set the input into 2 and connect the input with the signal generator and dot product. And then I browse another scope and I rename it as the scope 2 and I connect it with the path generator. We run the simulink, then we double click the scope 1 and we're gonna see the analog signal and the sample signal. Firstly, when I run the simulink, there are 10 cycles and I set the stop time into 3 and we see there are 3 cycles there. 1, 2 cycles and 3 cycles. So, the sample signal waveform is spiked. It is not quick. So, we need to change it by click at the model setting. We go to data import hotspot. We create the additional parameter and we set the refine factor to 250. We run again the simulink and double click at the scope 1 and we see the sample signal and there's no spike anymore. Then we look at the scope 2 that link to path generator and we see there are square signal waveform will shown. Then you press the uniform encoder and also for the scope. We connect scope 3 with the uniform encoder. For the uniform encoder, we need to set the peak to 1, the peaks to 3, and we need to click the side integer at the output type. Then we run the simulink and double click at the scope 3 and we see the waveform for the uniform encoder. Then lastly, we browse the uniform decoder and also for the scope for number 4 and we set the peak at 1 and the peaks to 3. Click OK. We run the simulink and we double click at the scope number 4 and we see the waveform for the uniform decoder. That's all for the question 3 example 1. Thank you.
So next, I will present how to produce the output sine wave of the second example by using the simulink. First, we use the signal generator, uniform encoder, uniform decoder, and scope with 2 input. Connect all the blocks as shown. Next, set the block parameter of signal generator, which is set the amplitude to 1, frequency to 1 unit in Hz. For encoder and for decoder, set 3 bits for both. Finally, run the block. This is the result of output sine wave without using compounding of 3 bits. Then we need to change the frequency from 1 Hz to 2 kHz. Change the bits of encoder and decoder from 3 bits to 8 bits. By changing to kHz, change the time base from 3 to 0.001. Run the block. So, this is the result output sine wave without compounding of 8 bits. Next, for 16-bit without compounding of 2 kHz, repeat the step by changing the parameter of uniform encoder and decoder from 8 bits to 16 bits. And run the block. So, this is the result output sine wave without compounding of 16-bit. Why? By using compounding, we need to add 2 more blocks for the compounding parts, which is a low compressor and low expander. For low compressor and low expander block parameter, set the MU value 255 and the peak signal magnitude to 1. Then run the block. So this is the result of output sine wave using compounding of 3 bits. Next, for 8 bits, repeat the step by changing the frequency from 1 Hz to 2 kHz. Then change the parameter of encoder and decoder to 8 bits. run the block. So this is the output sine wave using comparing of 8 bits. Lastly, for 16-bit, repeat the step by changing the parameter of encoder and decoder to 16 bits and run the blocks. So this is the output sine wave using comparing of 16 bits. At the end of this project, we have learned that passcode modulation (PCM) is a digital approach for transmitting analog data because PCM has only two potential states, which is logic 1 and logic 0. The signal in PCM are binary. The process of converting is known as encoding, while the decoding also involves retrieving the message from the binary numbers. It involves the detecting each new frame in the data stream, extracting the binary numbers from each frame, and producing a voltage proportional to the binary number.